Hi everybody! Today in this 5 minutes video, I will try to highlight and summarize the most important points of the first part of Unit 5, ligand substitution. Ligand substitution reactions consist in the substitution of a ligand from the coordination sphere of the metal by a different one, without the modification of the coordination number nor the valence electrons or the oxidation state of the metal. There are different mechanisms, but we are going to highlight only the extreme cases: dissociative mechanisms and associative mechanisms. Although there are many other situations which are also possible between these two cases, you have already studied these pathways with the corresponding factors affecting the rate of the reaction in Advanced Inorganic Chemistry 1, so I would not repeat them here. The dissociation mechanism, D, is usually encountered for 18 electron complexes, and there is an intermediate with a lower coordination number. In the case of 16 electron complexes, associative mechanisms can also be encountered, in which there is an intermediate with a higher coordination number. Let's also point out these other mechanisms really interesting, in which there is a change in the hapticity of a ligand prior to substitution. Remember, for example, that the allele group can change its hapticity from 3 to 1 or vice versa, and also the indonyl group, as we will see later, or also the nitrosyl ligand. This is an example of a substitution reaction in an 18 electron complex through a dissociative mechanism. One of the existing ligands, as you see, fall off. This opens up a free coordination site in an intermediate with 16 electrons, to which the neoligand can coordinate. If the mechanism were associative, the intermediate would be a 20 valence electron complex, which are rare. Dissociative substitution can also occur in 16 electron complexes if sterically bulky ligands are involved, as those in this example. Associative pathways are usually encountered in 16 electron complexes, being typical in square planar D8 complexes of palladium-2, platinum-2, and rhodium-1, as in this example. It starts with the association of the incoming ligand, trimethylphosphane ligand, to afford a pentacoordinated intermediate with a trigonal bipyramidal geometry, followed by the dissociation of one of the original triphenylphosphane ligand. We can make the chlorido ligand to go away by adding silver cation. As I told you at the beginning of the video, some 18 electron complexes can undergo an associative route if any of the ligands can change their coordination number. For example, linear nitrosyl ligand, cationic one, acts as a 3-electron donor, while it acts as a 1-electron donor when it is bent. That also happens with the indonyl ligand, which gives substitution reactions easily due to the indonyl effect. This effect consists in the ability of changing the aromaticity between the CP and their rings, thus changing from a coordination eta 5 to eta 3. Let's finish with one of the most important substitution reactions, which are those of the carbonyl ligand. Remember that these kind of reactions will always need photochemical or thermal activation or a decarbonylation agent such as trimethylamine oxide. Thank you very much for your attention, and let's start preparing the next video on oxidative addition and reductive elimination. Bye.